So today we're going to talk about section 4.5 with triangle congruence, and we're talking about ASA, AAS, and HL. What this means is angle, side, angle, 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 side, and hypotenuse leg. First, we need to talk about what it means to have an included side. When we talk about an included side, if we have a triangle, and I'm just going to go ahead and draw it this time, and if we have a triangle, and I mark two of these angles this way, the included side is going to be this one here. So if I have A, B, C, I could say that AB, the segment, is the included side between angle A and angle B, okay? Because it is between them. It's shared by both angles. And so when I go down to postulate 4.5.1, the angle side angle postulate, I find out that if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. So if I have the situation where angle A is congruent to angle D and angle C is congruent to angle F, and the side between those two angles, the included side, notice I've marked them included. If I have these three congruent relationships, then I can say that triangle ABC is congruent to triangle DEF by angle side angle. When I go down to example 2 here, notice I've skipped example 1 because it's in your book. It was a little confusing, so we might go through that one in class. But for example 2, we're going to determine if we can use angle side angle to prove that these two triangles are congruent. We're going to explain our answer. So let's write out what we know. We know that angle VXU is congruent to angle VXW. We also know that because this is a linear pair, this must be a 90-degree angle. So therefore, angle UVX is congruent to angle WVX. So I have an angle, and what I'm going to do is I'm going to try to prove something about the included side. Well, I see this included side here is XV, so I can say that XV is congruent to XV, and we remembered this from last video by the reflexive property of equality. Okay? And so what that means is I have an angle and a side, and they're in the relationship of angle, then side, then angle. So what I could say is that triangle UVX is congruent to triangle WVX by angle, side, angle. Okay? So that's how this works. In part B, you are going to be doing this. In fact, I'm going to allow you to pause, and so you can have the example up here and you can see how it works. You can try the exact same thing. Notice, I'll give you a hint. Use the properties of parallel lines. I'm saying this because they wouldn't bother to give you these parallel lines if you weren't going to use them. So go ahead and pause this video and try it on your own. I'm going to go ahead and keep rolling through so that you can see how the example works itself out. Let's look at it. I'm going to mark, using the properties of parallel lines, I'm going to mark what angles are congruent. And so using these properties of parallel lines, if I extended these, I would see that I actually have a situation where I have two parallel lines cut by a transversal. So that means that alternate interior angles must be congruent on both sides. And so I think it becomes easier to see what exactly we're going to be doing here. And so what I'm going to say is angle KNL is congruent to angle, so that was K and L, that was the one with 2, is congruent to angle MLN. That's my angle. I'm going to say that side or segment NL is congruent to segment NL. Reflexive property of congruence. Up here this should have been of congruence. You're right, I made a mistake. Reflexive property of congruence. So that's my side. And so I'm using angle, side, angle, so I need to say something about the other angle. So I used this one and this one. And now I'm going to use the angle with 1. So I'm going to say angle NLK is congruent to angle LNM. You see how this works. So that's my angle. So I can say that triangle NKL is congruent to triangle LMN by the angle side angle congruence postulate. Let's keep going on. The second one that we're going to learn about today is the angle side angle congruence postulate. Okay? Actually, this should say, I made a mistake. Angle, side, or AAS. It says if two angles and a non-included side of one triangle are congruent to the corresponding angles and a non-included side of another triangle, then the triangles are congruent. So what does this look like? I need to mark up my diagram a little bit. And so what I have is this. It's telling me that these two angles are congruent. It's also telling me that these two angles are congruent. The third piece to this is the unincluded side, which in this case is going to be outside of these. So what I'm going to say is that because I have two angles and a non-included side, so the key to this is the non-included side part. And they must be corresponding. So see, if I were to line these up on top of one another, it goes angle with 1 mark, angle with 2 marks, and the side. It goes angle with 1 mark, angle with 2 marks, and the side. They have to be in the same order. Okay? Let's look how this works. Down here we have a little bit of a proof. It's actually a pretty cool little proof because what we are going to do is use a theorem that we've previously used. Now, the thing about previously used theorems is, much like these two that we've learned today, you should have them in your note cards because we can refer back to them. So let's look at what we're given. We are given the facts that angle G is congruent to angle K. We can see that from our diagram. We are also given the fact that angle G should be angle J. That's a mistake. Angle J is congruent to angle M, also given. And we're also given the fact that HJ is congruent to LM. Okay? I marked them with a segment over the top so that I know what I'm talking about. Okay, so let's look. Basically what I'm going to do is I'm going to go through and prove something previous that's going to lead me to this conclusion. So eventually I want to be able to say this. So that's where I'm going. So let's look at what we can do. If I use these facts, I'm going to try to figure out something else that I can say about this triangle. Well, if I look back at my previous theorems, I can say that angle H is congruent to angle L because it's called the third angles theorem. And it basically says that if two angles in one triangle are congruent to two angles in another triangle, that the third one must be the same. Think about it. If this was 60 and this was 30, this one would have to be 90. And if this one's 60 and this one's 30, they would have to be 90. So the third angles theorem says that angle H is congruent to angle L. How can we use that? Well, now if I marked it on my diagram, look at what I've got. I'm going to mark it with 3 arcs. Now I have an angle, a side, and an angle. So what I'm going to say is that I am going to say triangle GHJ is congruent to triangle KLM, because I'm going to use a different theorem. I'm going to use the angle, side, angle theorem to say that they're congruent, because now I have angle, side, angle, congruent to angle, side, angle of another. It's pretty neat. It's a pretty neat little proof. Let's go down this way. We're going to talk about the way of the flow of this proof. We're going to use a flow proof for this. We're going to use angle, angle, side to prove that the triangles are congruent. Once again, they've given us parallel lines, so we're going to use those facts to kind of help us out. Let's look. If I know that these two lines are congruent, or parallel, I'm sorry, they kind of extend out this way, right? They wouldn't give us this fact if we weren't going to use it. Well, if I consider the line AE as a transversal, then I really have these two angles are congruent, because they're alternate, opposite sides of the transversal in between the parallel lines. So what I'm going to say is I'm going to say angle A is congruent to angle E because of alternate interior angles. Okay? Also, by that same token, if I consider this my transversal, then I can say that angle B is congruent to angle D. Also alternate interior angles. Well, now look what I have. If I have this angle here congruent to this angle here, I have two angles and a non-included side. So I can say that BC is congruent to CD, because that's given information that was in the diagram already. And so together these three pieces of information show me that triangle ABC is congruent to triangle EDC by the angle, angle, side theorem. There were a couple of different ways we could have done this. I could have shown that these were vertical angles and done angle, side, angle, but they wanted angle, angle, side. It's kind of a beautiful little proof right there. Okay? One last theorem. Go ahead and put this one in your note cards as well. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of another triangle, then the triangles are congruent. So you'll see, I have the hypotenuse. Recall, hypotenuse, side, opposite, the 90-degree angle. Okay? So I need a leg and I need the hypotenuse. So when I go down to example 4, I'm going to determine if these two triangles are congruent by using the hypotenuse leg congruence theorem. Can I determine if VWX is congruent to YXW? Well, let's look at what we've got. We have VW is congruent to YX because that's given. Okay? So that's my leg. And because triangle VWX and triangle YXW are right triangles, that's the definition of a right triangle. Notice they have a right angle in them. I can also say that WX is congruent to WX because that's the reflexive property of congruence. Now, so if this is congruent to itself, I have a hypotenuse and a leg of the two triangles. It might help you to draw these out. So what you would have is something like this. So this would be V, this would be W, this would be X, and my other triangle would look something like this. I would have, on my top here, I would have W, I would have Y, and I would have X here. Okay, do you see how this works? And so what I've shown is that VW and YX are the same. I've shown that WX is congruent to WX. So I have a hypotenuse and a leg of each of two right triangles. Another one, and the last problem that we will attempt on this, is to say that triangle VWZ is congruent to triangle YXZ. So let's draw those two out. VWZ, so this is going to be V, this will be W, this will be Z. I have a right triangle here. And I also have this other right triangle over here. That will be YXZ. So this is Y, and this is X, and this is Z. And what I can show is that YX is congruent to VW, but I can't find anything out about the hypotenuse, because here's the hypotenuse of one, here's the hypotenuse of the other. So no, not possible. No hypotenuse given. Okay, so up here we used hypotenuse leg. Down here we cannot use it. Thanks for watching, guys. If you have questions, remember to write them in the margin. Thanks. We'll see you next time.